Welcome to MEI Modelling with Algorithms. We're on the topic Linear Programming 2, Simplex method, and this is video 2.2, Application to Standard Problems. Now, we saw in the previous video an introduction to the Simplex method, and we're just going to recap a couple of things to start with here. So firstly, remember that the Simplex method can be used for problems with more than two variables. So the example we saw previously just had two, but we're going to see one with more than two now. And at each stage of the iteration we are somewhere within the feasible region, so we've got a valid solution, but it won't necessarily be optimal. We'll know when it becomes optimal after maybe several iterations, because we can see that there are no negative values left in the top row, in the objective row. And at the end of each stage, at the end of each iteration, we can interpret the algorithm in terms of a place where we're located within the feasible region. And what we saw previously was that we are moving from the origin where we start towards the optimal solution at each stage. Now, just a reminder of what the stages of the algorithm are then. The first thing is we have to formulate the problem using as a maximization problem using slack variables, and we transfer the coefficients into what's called the Simplex tableau. And it is important to make sure that the elements in the final column are non-negative, and we could ensure that by multiplying through by a negative number if we needed to. In terms of the top row, we then look at that and see which of the values in the top row is the most negative. Remember, if none of them are negative in the top row, then we don't need to do anything. We're already at the optimal solution. And so the most negative element in the top row tells us where the pivot column is. And then to find the pivot row, we do what's called the ratio test. So we take the ratio of the final element with the element in the pivot column, and we look for out of any positive numbers that we get, whichever one of those is the smallest, that will give us the pivot row and the pivot element. And what we need to aim to do then is make sure that after the iteration that we perform, that the pivot column has become a column which is entirely zeros apart from a single one in place of the pivot element. So we use that pivot row to reduce all the other rows to such that there's a zero in the pivot column. Then we essentially check again if there are any negative numbers in the top row. If there aren't, then we're done. Otherwise, we'll repeat the process until there are no negative numbers left in the top row. And then at each stage, including the final stage, we can interpret the tableau. The main thing to know, of course, is that the values on the right hand side give us the values of the non-zero variables. So this is the example we're going to look at, and the first thing that we need to do is to rewrite both the objective function and the constraints into a format that we can put into the tableau. So with the objective function, we make sure that everything goes on to the left, so we write that as p minus 6x minus 8y minus 10z. And then for the constraints, we keep them as they are in terms of the sides, but we deal with this inequality. We turn it into an equation by introducing what's called a slack variable. So this one we'll write as 2x plus 3y plus 2z. But then to make up this slack, to make up this difference between the left hand side and the right hand side, we add this slack variable. We'll call this S1, and now we can say that equals 10, and that's fine as long as S1 is greater than or equal to 0. That will ensure that this is a less than or equal to relationship still. And then we can do a similar thing for the other constraint, so that's x plus 3y plus 2z plus S2 is equal to 8. And again, this second slack variable s2, that must also be greater than or equal to 0. So we can see those equations are kept there at the top right for reference, and we can now put the coefficients into the simplex tableau. So for the objective row, we've got 1p. Remember, it's the coefficients, not the values, that go in here. We've got -6, -8, -10. Because there are no slack variables involved here, then they just have coefficients of 0. And the right hand side there is 0 as well. Then for the this constraint, well, p doesn't appear again, so p obviously has a coefficient of 0, and then we've got 2x, 3y, 2z, we've got 1s1, no s2s, and we've got a right hand side of 10, and then for the final constraint we've got 0, 1, 3, 2, 0, 1, and 8. So at this stage we can look at the top row. We see there are negative numbers there, and we take the one which is the most negative, which is this -10. So we have identified this as our pivot column. And then we do the ratio test. So I take the right hand side here, which is 10, and divide it by the number which is in the same row in the pivot column, which is 2. So we do 10 divided by 2, which gives me 5. And then here I do 8 divided by 2, which is 4. This one is the least of those, so this is going to be my pivot row. And so what I need to do now is I need to think about row operations, which are going to mean that when I'm down here, this column has become 0, 0, 1. So let's give some names to these rows, and we're going to require a number 1 there, which means that this row 6 will be row 3 divided by 2. So we take each number here and divide it by 2 to make row 6. So I've got 0, 1 divided by 2 is 0.5, 3 divided by 2 is 1.5, 2 divided by 2 is 1, and then we've got 0, 0.5, and 4. So that's the easy part out of the way. What I need to do now is think about how I can create zeros in these two positions. So for row 4, I have to start with row 1, the row that corresponds to row 4 above there. So I need to take row 1, and then I need to either add or subtract some multiple of the pivot row. Okay, now I can use either the pivot row as it was, or I can use this one because they're both multiples of each other. It's probably going to be easiest here. I need to add 10, so if I add 10 lots of this, that will do the job. Okay, so I'm going to say this is row 1 plus 10 times row 6. So I've got 1 plus 10 lots of 0, so that's obviously just 1. Then minus 6 plus 10 lots of 0.5 gives me minus 1. Minus 8 plus 10 lots of 1.5 gives me 7. Minus 10 plus 10 lots of 1 obviously gives me 0, which is what I required. Then I've got 0 plus 10 lots of 0, 0 plus 10 lots of 0.5, and 0 plus 10 lots of 4, which is 40. Then we're going to do a similar thing for row 5. You might want to think yourself about what's going to happen here. If you want to pause the video, and I'll reveal the answer in a moment. Alright, so there it is. So you should have decided to either do row 2 minus row 3, or you could have done row 2 minus 2 lots of row 6. It means the same thing. And these are the numbers that you would have got for that row there. So now we'll look again at what we've got, and especially this top row. we can see there is still one negative number in there, so we need to keep going. We're not yet finished, and that means that this of course is going to be our next pivot column. And so now we can perform the ratio tests again. So I do 2 divided by 1, which is of course 2, and I do 4 divided by 0.5, which is 8. So clearly this row is the one with the least positive result, so this is going to be my new pivot row. And my aim then is to make sure that the next in the next iteration that this column here ends up with a 1 in this position and then zeros everywhere else. Now the nice thing I guess here is that we've already got a 1 there, so I don't need to change anything about this row to make row 8. So row 8 will simply be equal to row 5, and then row 7 needs to be made from row 4, and row 4 has a value of -1 in that position at the minute, so I want to add 1 onto that. So if I just add row 5 or row 8 on to that, that will achieve that result, and so that gives us these numbers. So every time we're just doing row 4 plus row 5, so that gives us 1, 0, 7, 0, 1, 4, and 42. So now we just need to create row 9. Again, if you'd like to pause the video at this stage and try and do that one by yourself on paper, that would be a good idea, and I'll reveal the answer in a moment. And that's what you should have got doing row 6 minus 0.5 lots of row 5 will give you the 0 there, and those are the values you should have got for the other elements. And what you can see now is that in that top row there are now no negative numbers, so we know that we've now found the optimal solution and we can stop. So now we're going to turn to the question of interpreting the Simplex tableau at each stage of that process. So that's what it looked like initially, and if you remember what we've talked about in the previous video, in any state that the tableau is in, we can identify 2 different types of variable. The first type that we're going to talk about are these. I'm going to highlight the columns to help you to see what's going on there. And these 3 variables at this stage, if I look at the numbers, they're all zeros apart from a single 1. And those are called basic variables. And we interpret the tableau such that the basic variables have values equal to the number that's on the right hand side in the same row as the number 1. So P is equal to 0 at that stage, and then the slack variables S1 and S2. S1 is equal to 10, S2 is equal to 8. Any other variables, so anything that's not a basic variable, is a non-basic variable, and they have a value of 0. So X equals 0 at this stage, Y equals 0, and Z equals 0. And with the simplex method, that's always the case to begin with. We're starting at the origin, and the objective function is equal to 0 at that point. Once we've done one iteration though, things have changed. Alright, we've now got, well, P is still a basic variable. It turns out P will always be a basic variable. But look what's happened here. It's now Z and S1 that are the basic variables. Alright, So S1 now has a value of 2. S2 is now non-basic, so S2 is now 0. X and Y are still non-basic, so they are both still 0. And P is equal to 40, because P is always a basic variable. Now that number there has moved up to 40, so at this stage P is equal to 40. So we've increased the value of the objective function, which is what we're aiming to do, of course. X and Y are still both equal to 0, but Z is now equal to 4. So what we could do, we can interpret this. We're moving in three-dimensional space. We've moved along the z-axis by 4 units, and in doing so we've increased the objective function from 0 to 40. And then after the final iteration, things have changed again. P, of course, as we said, still basic variable. P is now equal to 42, so it's increased again. It's now at its maximum possible value. And the other basic variables now are X, Z, and that's it. So there's actually no slack left at all. Both the slack variables are now equal to 0. That's sometimes happens, it doesn't always happen. So sometimes if the slack variables are left with some non-zero value, we can interpret that in terms of leftover resources perhaps. But in this case we've been very efficient. We don't have any slack, we haven't got any waste, and so we've just got X is equal to 2. Y is still non-basic, so that just means that Y is equal to 0 even in the final optimal solution, and Z is equal to 3. So in going from this stage to this stage, we've moved in both the X and Z direction. So we've sort of moved in the XZ plane to this point, the point with coordinates 2, 0, 3. That is our optimal solution with a value of objective function equal to 42. So just to summarize then what we can say about the simplex method, it's certainly reliable. It allows us to deal with more than 2 variables, which would be difficult graphically. It's also, and this is going to be the subject of the later half of this topic, it's very easy to put this into a computer. We've got a table of numbers. Computers are good at handling that kind of thing. What we haven't seen yet, but we're going to see in the next video, is how we can adapt it slightly to deal with what we might call non-standard problems. So some of the restrictions that we've been mentioning can be relaxed if we adapt the algorithm somewhat. And then again, turning to the second half of this topic, the 3 videos which form the second half, we're going to talk a lot about how we use technology. We're going to look at some various linear programming software that will help us with that, because in practice that's how we're going to want to do it. We certainly don't want to be doing all this work by hand that we've been seeing so far. And these things are widely available for use. They're freely downloadable. They're reliable. There's choice out there. Some are are better than others at certain things. So you'll get a flavour of what's out there over the course of those 3 videos, which are coming up shortly. So that concludes video 2.2, application to standard problems. Next video will be 2.3, application to non-standard problems.